Yeah, make sure you reload the page at least once before the handout is accessible. All right, you want to get started, maybe?
Yeah, sure, I'll get started. Thank you everybody for joining us today. Today we're going to be covering sequences and summations. So there's two types of sequences. The first type we'll be covering is arithmetic sequences. An arithmetic sequence is a sequence of numbers for which the difference between each two consecutive terms is constant. So um, the general form of an arithmetic sequence is a plus d, a plus 2d, a plus 3d, so on until a plus n minus 1d, where n is the nth term. And for this is for two constants or two numbers, a and d. And d is referred to as the common difference. So let's walk through some examples. This is the first example. 1, 2, 3, 4, 5, 6, 7. This is an arithmetic sequence, and the length of this is 7, and the common difference is 1. And this is because the difference between each consecutive term, so for example, between 1 and 2, 2 and 3, 3 and 4, 4 and 5, and so on, is 1. And it's an arithmetic sequence because the difference between each term is constant. It's 1, 1, 1, 1, so on. Another example of an arithmetic sequence is 2 thirds, 7 thirds, 10 thirds, so on. And this is an arithmetic sequence of length 4, and it has a common difference of 5 thirds. And one more example of an arithmetic sequence that we have is 17, 12, 7, and 2. And this is an arithmetic sequence of length 4 because there's 4 terms. The common difference is negative 5. So as you can see, the common difference can also be negative.
And yeah, we actually have a quick typo. On the second bullet, it should be 12 over 3, which is 4. But yeah, the common difference is 5 thirds because at each step it increases by 5 over 3. So just change that typo in your mind and it'll all be good.
All right. And like Ram said, just pretend that in the second example, it's 12 thirds instead of 10 thirds. And in our last one, as you can see, the common difference can also be negative, and the arithmetic sequence can also be decreasing. And in this case, we have 17, 12, 7, and 2, where each term is 5 less than the previous term, and that makes it an arithmetic sequence. And then one example of a sequence that's not an arithmetic sequence is 17, 12, 2, 7, because the common difference is not constant. The difference between 17 and 12 is 5, and between 12 and 2 is 10. And since 5 is not equal to 10, this is not an arithmetic sequence. All right, the next type of sequence we have is called a geometric sequence. So a geometric sequence is a sequence of numbers for which the quotient between each two consecutive terms is constant. So the general form of a geometric sequence of length n is ar, ar squared, ar cubed, all the way up to ar to the n minus 1. And this is for two numbers a and r. And in geometric sequences, r is referred to as the common ratio. So
And
let's look at some examples.
yeah, but before you say it, I just wanted to say the reason it goes up to n minus 1 is because we're saying that the geometric sequence has n terms. So you can think of the initial term as instead of being a, it's a r to the 0. So it's r to the 0, r to the 1, r to the 2. And in order to have n terms, it must end at n minus 1, not at n. So we're imposing that the length is n. That's why it ends at ar to the n minus 1.
All right. So our first example is 1, 2, 4, 8, and 16. And this is a geometric sequence of length 5 with a common ratio of 2. So in this example, we look at the general form. A is equal to 1 because the first term is 1, and the common ratio is 2 because 1 and then 1 times 2 equals 2, 2 times 2 equals 4, 4 times 2 equals 8, and so on. And adding on to what Ram said, if you look at our last term, 16, well, this is the fifth term, so it's 1 times 2 to the 5 minus 1, which is 1 times 2 to the fourth, which is 16. So we can see this to be true. Another example we have is 1, 1/2, 1/4, and this is also an arithmetic sequence of length 3, and the common ratio is 1/2. Because we multiply by 1/2. Yes.
Geometric, but
Geometric. Oops. Pretend there's a typo there too. Arithmetic should be geometric. So the common ratio is 1/2 because we multiply each term by 1/2 to get to the next term, and the common ratio is 1/2. So 1 times 1/2 is 1/2. 1/2 times 1/2 is 1/4. So in all sequences, one really important thing to note is that the ordering matters. The order of the numbers always matters in sequences. So first we can look at an arithmetic sequence. An arithmetic sequence is either constant, in which case the common difference is 0. So an arithmetic sequence could be 5, 5, 5, 5, 5. And this is an arithmetic sequence because the difference between each term is 0. And this is what we call a constant arithmetic sequence. Another arithmetic sequence is strictly increasing, and this means that the common difference is positive. So between the terms, we increase, and the common difference is positive. So 1, 2, 3, 4, 5, 6, 7 is a strictly increasing arithmetic sequence because the common difference is 1, and we increase between terms. And the third type we have is a strictly decreasing type of sequence. And this means that all the terms are less than their previous terms, where each term gets smaller and smaller and smaller. So an example of this is 7, 6, 5, 4, 3, 2, 1. And this is strictly decreasing because the common difference is -1, and we get smaller between each term. Looking at geometric sequences, we also have a constant sequence, in which case the common ratio is 1. So for example, 5, 5, 5, 5, 5 could also be a geometric sequence because the common ratio is 1, because we multiply 5 by 1 to get 5 again, multiply by 1 to get 5 again, and so on. The other type of sequence we have is strictly increasing, and this also means that our terms are increasing, and strictly increasing would mean that the common ratio is greater than 1. So if the common ratio is 2, 3, 4, so on, it's strictly increasing. One example that we saw is 1, 2, 4, 8, 16. And this is strictly increasing because the common ratio is 2. And finally, we have strictly decreasing. And this is when we get smaller and smaller, and each term is less than the previous term, just like an arithmetic sequence. However, this means that the common ratio is less than 1. So for example, the common ratio is 1/2. This means that we are strictly decreasing because each term is 1/2 of the previous term, or each term is less than the previous term. All right, now we will practice one problem.
all right. Yeah, I'll share screen now. And yeah, somebody's pointing out that in the chat that we can also have geometric sequences with a negative ratio. So if you have the ratio being more than 1, then it's increasing, like Nivet said. If it's the ratio is less than 1, then it's decreasing, like 1/2. But we can also have a negative ratio. So if the ratio is, say, like -2, then a geometric sequence, an example of a geometric sequence is 1, -2, 4, -8, 16, -32, and so on, because at each time you're multiplying by -2. So a good way to think about arithmetic sequences and geometric sequences in general. So for an arithmetic sequence, the definition might be a little confusing, but basically what you're doing is you're starting with a number, the first term, and then you're adding the same number over and over and over. That's why the common difference is always the same. You're adding the common difference over and over. So that's why it's like a, then a plus d, then a plus 2d, and so on. And for a geometric sequence, it's also really intuitive. You start with a number and you multiply the same number over and over, not the initial number, but a common ratio. So a and then a times r squared, and so on. So let's apply all this theory to an actual problem that appeared on the AIME. So we have two geometric sequences, A1 through A1, A2, A3, and so on. So these sequences can also go infinitely. They don't have a specified end, but they just you keep adding on, or you keep multiplying on in this case. We're given that they have the same common ratio, and we're given their initial two terms. So we're given A1 is 27, B1 is 99. And finally, we are given that the 15th term of the first is the 11th term of the second. The question is to find the 9th term of the first sequence. So this can be solved using the theory we've mentioned, but take a couple minutes to try and solve it on your own. And then we'll come back and see how to do it. And yeah, if you get the answer, or if you have any questions, feel free to direct message any of the teachers. In particular, don't send it to everybody.
Yeah, I don't think they can chat publicly anyway, so yeah, just send it to one of us.
Why don't you take about another minute or so? We'll get back at 5:15.
Someone's saying we didn't post last week's recording. Did you do that? Or
Oh yeah, it's on YouTube. I haven't uploaded it to the spreadsheet yet, but I'll do that as soon as possible. Oh, so someone's asking what does oh, this is a bit confusing. It's a sub 9. That's not a letter. Okay, let's go through how to do this problem. So again, we're given two geometric sequences with the same common ratio, and we're given that the 15th term of the first is the 11th term of the second, and we're given the initial two terms. Well, let's say, so we're given a lot of information actually. We're given the initial terms, and we know the common ratios are the same. So we can actually just write down what the sequences will be. So let's define R to be the common ratio between terms. So for the two geometric sequences, R would be the common ratio for both of them. We're given that it's the same for both. So let's define that to be R. Now, the first term in the first and second sequences are 27 and 99 respectively. So now using this information, we have the common ratio, the first term, and we have the common ratio, which means we can just write down what the general term of the first geometric sequence will be. So let's just start with some small cases. So we have A1 is 27, that's given. A2 we multiply on by R. Remember, the common ratio just means we're multiplying by that number each time. So A2 is 27 times R. A3 is 27 R squared because we multiply by R. So in general, you can see that A sub n will be 27 times r to the n minus 1. Now, n minus 1, even if you don't have to, you don't have to go through that entire logic of ar to the 0 and so on and counting. You can just infer from small cases that, okay, a2 is 27r to the 1, a3 is 27r to the 2. Now you know it has to increase by 1 each time, which means an will just be 27 times r to the n minus 1. So it's sort of like pattern matching, where you know you just have to get it to within an off by 1 errors kind of thing. And you already know that a3 is 27r to the 2. So you know it'll extend to be 27 times r to the n minus 1. Similarly, b is no different other than the first term. So b sub n will be 99 times r to the n minus 1. That's just because the first term is 99, whereas it's 27 in the first one. All right, so what's the plan now? Now we have the general term of each. The only condition remaining is that a sub 15 is b sub 11. So we can set up an equation. A sub 15 in particular, we can write down from this general formula. It's 27 times r to the power of 14. Similarly, b sub 11 is 99 times r to the power of 10. So we can set these equal and solve for r. So we have 27r to the 14 equals 99 times r to the 10. Yeah, like Suresh is saying, the most important part of this problem is setting up the geometric sequence and finding the general term, specifically finding a sub 15. From there, it's a computation. But so let's just go through that. We have this equation from a sub 15 is b sub 11. So now we can use this to solve for r. In particular, we can divide by r to the 10 from both sides. So we get 27 times r to the 4 is equal to 99. If we divide by 27, we get r to the 4th is 11/3. Now, you don't even have to write down r as the 4th root of 11/3. That would be helpful, but it turns out we only need r to the 8th because the question asks us to find a sub 9. Now, if we go back to this general formula, a sub 9 is simply 27 times r to the power of 8. So 27 times r to the power of 8, a1 times r to the power of 8. And we're given r, and we figured out r to the 4th is 11/3. So it's 27 times 11/3 squared, which is 363. So just to recap, the main idea was to just let r be a variable, which is the common ratio. And then we can find the general terms in both sequences, analyze this condition, solve for r, and finish the problem. So this problem is a good practice with geometric sequences and multiplying to find the general term. All right. Now we're going to transition to a different topic, which is also about sequences, the mean, median, and mode. Nivid, you want to take it away?
All right, I didn't realize I was muted. So first we're going to go over mean. So when we have a sequence, any type of sequence or set of numbers, this extends into any set of numbers that we have. It doesn't have to be an arithmetic or geometric sequence. Now we're just kind of expanding into any set of numbers in any order. Then one thing we look at is the mean. So given a list of numbers, the mean is the average. So we take the sum of all the numbers and divide by how many numbers there are. So the general formula for the mean is if we have a bunch of numbers a1, a2, all the way to an, where n is the nth number in the set, then the mean is a1 plus a2 plus a3, all the way up to a to the n, divided by n. So one example we have is, let's say we have the set of numbers 5, 6, 3, 3. So there's 4 numbers. So in order to find the mean, we had to add the numbers together, 5 plus 6 plus 3 plus 3, and then we divide by the number of numbers, and the number of numbers is 4. So the total sum is 17 divided by the number of terms, 4, and that gives us the mean, which is 17 over 4. The next thing we have is the median. The median is the middle number in a set of numbers when we order the numbers in a non-decreasing order. So this means that, let's say we have a set of numbers 5, 3, 4, 2, 2. So the median of the set is 3, and we can find its 3 by first ordering it in a non-decreasing order. The reason we say non-decreasing order rather than increasing order is because we might have two of the same number. So for example, we have two 2's, and these two 2's will go to the front, and these will be the first two because these are the smallest two numbers out of all the sets of numbers. Then we have 3, 4, 5, and this is how we list them in a non-decreasing order because we don't decrease from one number to the next. Now we can just find the middle number, which is the number 3, so our median must be 3. If there are an even number of numbers in this set of numbers, then the median is the average of the middle two numbers. This is because there isn't a unique middle element, so we just find the kind of average of the middle two elements. So one example of this is 2, 2, 3, 4, 5, 5. And this has an even number of elements, so we can't really find a number that's in the middle of everything. So we find the two middle numbers, which are 3 and 4, and we find the mean of them, or the average of them, which is 3 plus 4 divided by 2, which becomes 3.5. The last kind of data analyzing thing we're going to go over is called the mode. And the mode is the number that appears the most often. And one way that I remember this is by thinking mode starts with MO, and MO stands for most often. So mode just means the most often. So for example, if we have a set of numbers like 2, 2, 3, 4, 5, the mode is the number 2 because 2 appears twice, whereas all the other numbers appears once. So the number that appears the most often is the number 2. If there's a tie for the number that appears the most, then we say that it has no unique mode, which just means that there might be two 2's and two 3's and one 4 and one 5. In that case, there's no unique mode. There's two numbers that appear just as often, so there's no unique mode. So for example, in this scenario, we have 2, 2, 3, 4, 5, 5, and this has no unique mode. All right, now we're going to go over an example. The mean, median, and mode.
No, I was just gonna say, yeah, Nivid, you do this example. I'll do the next one.
All right, sounds good. So the mean, median, and mode of the 7 data values 60, 100, x, 40, 50, 200, 9 are all equal to x. What is the value of x? So why doesn't everybody take a couple minutes and try it on their own? All right, so somebody asked a question in the chat, a pretty good question. But yes, the mode will be unique. There will be a unique mode in this problem. All right, I will start going over the walkthrough and the solution, but if you're still working on it, you can still work on it a little bit if you want. So since the problem gives us that the mean is x, we can set up an equation to solve for x. So if we look back at the equation, we can note that the fact that the median and mode are also x doesn't really help us with solving the problem. This information about the median and mode was extraneous. And extraneous just means that it wasn't useful and it was just kind of fluff that the problem added in to distract us from solving the actual problem, to make the problem seem more complicated than it actually is. So in this example, we can just forget about the fact that the mean and the median and the mode are both equal to x. We can focus on the fact that the mean is equal to x. So since the x is equal to mean, we have x equals, and then here is our formula for the mean. So the mean is the sum of all the numbers divided by the number of numbers. So the sum of all the numbers is 60 plus 100 plus x plus 40 plus 50 plus 200 plus 90 all over 7 because there's 7 data values. And combining the terms, we have x equals 540 plus x all over 7. So therefore, if we solve for x, we get 7. We can multiply both sides by 7 to get 7x equals 540 plus x. And this results in x is equal to 90. All right.
All right. Now, all right, I'll screen share. Wait, can you screen sharing? All right, yeah. So that was a good problem. Now we're gonna you can stop now. All right, now we're gonna go through another example, which is also about means and medians. This one was from the AMC 10B just a couple of years ago. This one's a bit more complicated than the one we just did because we actually have to think about the median and median and mean a bit more. But the question is for which, what is the sum of all real numbers x for which the median of 4, 6, 8, 17, and x is equal to the mean? So we have this list 4, 6, 8, 17, and x. Find all x for which the mean and median are equal. So take a few minutes to try it on your own. Again, this one is a bit harder and a bit more caseworky than the one we just did. But yeah, just try it. All right, we'll wait another minute or two, and then we'll get started. Again, if you have any questions about this problem, then feel free to direct message one of us. All right, so I'll just I'll start with explaining this problem. So the main issue here is that we have, so the mean we can always compute regardless of the order. It's just the sum divided by the number of terms. But the median is the tricky one here. We don't know what x is, but we do know that the median and mean are equal, which means we have to find the mean somehow. Say x is like 1,000,000, all right? Then we have 4, 6, 8, 17, and 1,000,000. So then the median would be the middle number, which is just 8, right here. But say x is negative 1,000,000. Well, in that case, it would also be 8. But say x is 7, then it would be 4, 6, 7, 8, 17. So the median would be 7. Similarly, yeah, so as I was saying, if x is negative 1,000,000, then it'd be negative 1,000,000, 4, 6, 8, 17. So the median is 6. The point is that where the position of x relative to these numbers affects what the median of these numbers can actually be. So we have to make cases based on, think about putting 4, 6, 8, 17 as sort of blocks on the number line, as sort of like red marks. We have to see where x lies in between the red marks or on either side of them to find what the median is. So in particular, this what I just said might be a bit confusing, but the cases are if x is less than 4, x is between 4 and 6, x is between 6 and 8, x is between 8 and 17, or x is bigger than 17. Those 4 cases encompass, and when I say between, I mean it could also be equal to those numbers. So between means inclusive. Now this encompasses all cases, and it will allow us to be able to compute the median for each case, because the point of making these cases is that in each of these cases, we now have imposed the order. We now know exactly what the order of the 5 numbers is in increasing order, which means we can now pin down the median. Over here, where we just have x, like I demonstrated, we cannot just find the median directly. All right. So like I said, we have the cases based on where it is in between these numbers. For each case, we have to check if there's a solution for x for which the mean and median are equal. So it's possible that in some cases, when we set the mean and median to be equal, we don't get any solutions for x. If that happens, then that case, there's no solutions for x in that case. All right. So first note that the mean, like I said, doesn't depend on where the position of x is. The mean is always 4 plus 6 plus 8 plus 17 plus x all over 5. And that turns out to be 7 plus x over 5. All right. So case 1, x is less than all of these numbers. Well, then the order of the numbers in increasing order is x, then 4, then 6, then 8, then 17. So the median is the middle value. Conveniently, by the way, there's 5 numbers. So we don't have to deal with the whole average of middle sort of thing where if there's an even number of numbers, then we take the average. So here there's just an odd number, which means the middle number is well defined. So the median in this case is 6. The mean was 7 plus x over 5. So setting these equals gives us 7 plus x over 5 is 6. And solving this, you get x equals negative 5. But yeah, so since negative 5 is less than or equal to 4, that means that indeed this is a case. This is a valid possibility. For example, if this equation spit out a value x equals 1,000,000, well then this case would be impossible, because the only way for the point would be that if this spits out x equals 1,000,000, then 1,000,000 is not less than or equal to 4, so it doesn't even fall in this case. We wouldn't even be able to get this order. We're sort of juggling with 2 restrictions here, which is that 1, x is less than or equal to 4, and 2, the mean and median are equal. So if these don't match up, then we know this case cannot work. But in this case, it worked. So we had negative 5, which works. So negative 5 is one value, which works. Now let's continue on. So there's less than or equal to 4. Now there's between 4 and 6. So case 2, x is between 4 and 6, again inclusive. So you can have the endpoints. Then the order of the numbers, now x shifts up 1. It's 4, 6, 4x, 6, 8, 17, because x is in between. So the median is 6. Now this is the same analysis, because in the previous case, remember, we also had the median was 6. So we're going to get x equals -5. But now x equals -5 does not lie in this range. So there we had a restriction that x is between 4 and 6. And that gave us that this was the order, which gave us that if the mean is equal to the median, then x is -5. But this is not a possibility because -5 is not in this range. So these brackets just mean 4, 6, which is in between 4 and 6 inclusive. So this case is impossible. We cannot have any solutions for the mean equaling the median if x is between 4 and 6. All right. Now let's do our third case, which is that x. Yes, by the way, like Suyash is saying, yes, we could have clumped the first and second case together. That's actually a good point. The reason is that the only reason we are splitting into cases in the first place is so that we can pin down the median. And in both of these cases, the median is 6 because x either appears x either appears before the 4 or after the 4, but the middle value is still 6. And the point is that we'd have x equals -5 in both cases, and we'd get that valid possibility. But let's stick to this analysis. So case 3. Case 3 is that x is between 6 and 8. In that case, the order of the numbers would be 4, 6, x, 8, 17. Now, in this case, the median is not 6. The median is x. We can say this because we imposed that x is between 6 and 8. Now, the median is x. The mean was still 7 plus x over 5, so we set them equal. We're going to test if there's actually a value which works. 7 plus x over 5 equals x. Then we can solve this equation. 7 equals 4/5 of x. So x equals 35 divided by 4. But there's an issue here. 35 over 4 is 8.75, which is bigger than 8. And as you can see here, we had the restriction that x is between 6 and 8. So the second, the restriction that the mean equals the median gave us that x is 8.75, which is not in this range, which means this case is impossible. Does that make sense to everybody? The fact that we're sort of splitting into cases to pin down the median, and then we're setting the mean equal to the median. But if there are no solutions, then we simply do not have that any value in that case is possible. All right. Now the numbers are, yeah, so 35 over 4 is bigger than 8. All right, so remember the numbers were 4, 6, 8, and 17. So we tested out less than 4. We tested out between 4 and 6. We tested out between 6 and 8. Now we have to test out between 8 and 17. So x is between 8 and 17. In that case, the order of the numbers is 4, 6, 8, then x, then 17, because x is between 8 and 17. Again, we're writing these numbers in increasing order. Like Nivid said a few slides ago, the order of the numbers really matters when you're trying to find mean and median and medians and that sort of stuff. So that's why we have to do these cases. In this case, the median is 8. The mean was still 7 plus x over 5. So setting this equal gives us 7 plus x over 5 is 8. So x over 5 is 1. So x is 5. But this is bad because 5 is not in between 8 and 17. So that means that there is no value of x in between 8 and 17 for which the mean is the median. If there did, then we would have x equals 5, but x equals 5 doesn't even lie in the range. If this logic doesn't make sense to you, I agree it's a little confusing, then please ask us or refer to the handout. Try to just work through it, see exactly why each case is failing. All right, now we have our final case, which is that x is bigger than all the numbers. So x is bigger than 17. Yeah, so again, just do the handout. If it's confusing, then refer to the handout after the class, try to understand it more, or you can refer to it right now and keep listening. So make sure you just make sure you understand at some point. All right, so x is bigger than 17. Then the ordering of the numbers is 4, 6, 8, 17, then x. Again, we could have clumped this with the previous case because the median is still 8. So the median is 8. Now the mean is still 7 plus x over 5. So we get x equals 5. But 5, again, is not bigger than 17. We could have clumped this with the previous case. It still wouldn't have worked. So there are no solutions in this case. So let's recap. Case 5 had no solutions. Case 4, impossible. Case 3, also impossible. No solutions in that case. Case 2, impossible. And case 1, we had x equals -5. So that means the sum, the question asked for the sum of all values. It was sort of tricky. If they just said there's just one possible value which works, if they told you that, then after testing this one, case 1, you wouldn't have moved on. But they're sort of trying to make sure you go through all the cases. But there does end up just being one value which works, which is -5. So the sum of all values is -5. All right. So the logic in this problem was a bit confusing, but make sure you just understand that we're trying to split into cases so that we can figure out exactly where x is, which will tell us what the median is, and then setting the mean equal to the median, we can see is there a valid value of x that works in the range. All right. So this is a pretty good problem relating the mean and the median. And generally with medians, you want to split into cases so that you can figure out the exact ordering. With mean and mode, you don't need to order it. It's always the same no matter how you order it. But median really depends on ordering, which is why casework sometimes comes into the picture. So this was a pretty representative problem of how some of those problems work. All right. Now we'll talk about sums in sequences. So Nivid, you want to talk about that? You're on mute.
Sure.
Okay.
Sure. I'll talk about that. And before we quite move on, there's some questions in the chat about this. Like Karam kind of said, in our scenario, in this specific problem, only case 1 worked. But if the numbers were a little bit different, there's a possibility that case 1 and case 5 could have worked. And if multiple cases would have worked, then we would have had to add them together. So there's not really one case which is the right case, but rather there's only specific problem. So for that reason, we only had to add -5 to the total sum. That's why negative. All right. So the next thing we have is sums and sequences. So a classic problem is to find the sum of the numbers in an arithmetic or geometric sequence. We will not deal with the sum of geometric sequences in this handout, but we will cover it in a later handout just because it's a little bit more tricky and a little bit more complicated. But in this, we cover the sum of an arithmetic sequence. So there's an important trick which helps us to find the sum of an arithmetic sequence. The sum of an arithmetic sequence is equal to its number of terms times the median of the sequence. So we're not going to prove it in class today, but it is in the handout if anybody wants to know why this is true. So if we 1, 2, and 3, easily find the sum. 1 plus sequence, if we have a bigger arithmetic sequence, like 1 plus 2 plus 3 all the way to 100.
I mean, Nivid, you're breaking up. I don't know.
Nivid, you're lagging and breaking up a lot right now.
Let's see.
It's
Oh,
frozen right now.
Yeah, your video is a bit frozen as well.
Maybe
all
Ram.
right, Ram, do you want to take
Okay,
over
yeah,
with that?
I'll explain this. Do you want to stop screen sharing, Nivid?
Yeah.
Yeah, no, so Nivid was totally saying just that when we want to find the sum of the numbers in an arithmetic sequence, there's a trick to do that, which is, so the numbers in an arithmetic sequence are, say, like 2, 4, 6, 8, 10, so on. And there's a very important trick which often helps with finding the sum. So again, this only will work when we deal with geometric series. We're going to cover the sum of an infinite geometric series, but here everything is finite. So there's an important trick, which is that the sum of an arithmetic sequence, so a plus d, a plus 2d, all the way till a plus n minus 1 times d, so an arithmetic sequence of length n, is equal to its number of terms, so that would be n, times the median of the sequence. Now, this often helps when you don't exactly know what the common difference is or the first term, but you somehow can figure out the median. So this trick does help a lot. You can prove this using algebra and other techniques, but just it's nothing too fancy. You basically just write out the sequence to be a plus d, a plus 2d, and so on. You find its sum. The proof is covered in the handout, which is on the website, but we're not going to cover it here. Just know that this trick exists. So if we're trying to find sums in arithmetic sequences, then it's going to equal to the number of terms times the median of the sequence. All right. Again, this only works for finite. So now let's go over a final problem, which is from the AIME a few years ago. It's about sums, and it's a bit complicated. It's a lot to look at because of all the timeses and pluses, but take a few minutes, try and understand the problem, and we'll come back. So basically we have a and b, which are 1 times 2 plus 3 times 4 plus 5 times 6 and so on. And then we sort of switch the order a little bit of how the pluses and times appear. So the question is to find their difference. This will not necessarily use like the exact theorem / theory for arithmetic sequences and so on, but that sort of background is very helpful for what we're gonna be doing. So the hint for this problem is try to minimize the amount of work you have to do. So don't, it's possible to compute A and B separately, but try instead, the question asks for the difference between A and B. The positive difference between A and B just means the difference, whichever one is positive. So for example, the positive difference between 5 and 7 is 2. You could say 5 minus 7 is -2, which is why we say positive difference. So the hint is to try to minimize the amount of work you have to do by taking advantage of all the similar numbers. So find A minus B absolute value, and we'll come back in a minute or two. This problem is it is a pretty tricky problem relative to what we've covered so far, but yeah, just take a couple minutes and then we'll go through how to do it. All right. If you're still working on the problem, keep working on it. But for the sake of time, we're gonna go over the solution now. So Nivid, you want to take that over?
All right. We're gonna start working on the solution now. So we have that a equals 1 times 2, 3 times plus 3 times 4 plus 5 times 6, all the way up to 39. And we have b equals 1 plus 2 times 3 plus 4.5, all the way up to 38 times 39. So we will find b minus a without computing these two separately. So a lot of times when we see problems like this, they seem really complicated, and we could try to find out what a is equal to and what b is equal to, but often there's a more clean technique and there's a much better technique where we don't have to go out of our way and compute two giant numbers, and rather we can just combine the two numbers before and see how they fit together, and then we can see what the final answer is. So when we subtract b minus a, we have this sort of equation here. So we've sort of lined up b over a in a way that kind of puts the two together. So the in b we have 1 plus 2 times 3, and the 2 times 3 we can temporarily align with 1 times 2. And then we have 4 times 5, which we can align with 3 times 4, all the way up to 38 times 39, which we can align with 37 times 38, and then on the an extra 39. So now if we go column by column, each term from the kind of gives us this equation on the bottom. So you see that we have 2 times 3 minus 1. The answer is 2 times 3 minus 1. And similarly with the third column, we can say that, and we can do this with each column, making it some number 2, 4, 6, so on, times the number greater than that and the number less than that. And then in the end, we have an extra 39, so we just subtract 39. Ram, do you want to take over from here?
Sure. All right. Yeah. So as Nivid said, the main idea is to sort of line them up like this. We did shift the pluses and times sort of, but if we line them up like this, we have 1 plus 2 times 3 plus 5, 4 times 5, all the way till 38 times 39. And then we subtract 1 times 2, 3 times 4, 37 times 38. And then we subtract this 39. So when we subtract, this 1 just comes down. Let me see if I can. All right, cool. So yeah, if we subtract, then the 1 just comes down and we just have 1. Now 2 times 3 minus 1 times 2. Well, that's 2 times 3 minus 1. We can distribute it that way. We can factor it. Similarly, this column, we're calling these columns, these blocks of 2, then blocks of 2, and so on, because they have a common number, so we can factor. If we subtract these, we have 4 times 5 minus 3 times 4, which is 4 times 5 minus 3. And if we keep going, it'll be 38 times 39 minus 37. Again, we're doing minus because there's a minus here. Everything is in the minus. And finally, we subtract off the 39. So now b minus a is equal to this thing right here. What's so nice about this? Well, the fact that 3 minus 1 is 2, 5 minus 3 is 2, 39 minus 7 is 2. All of the numbers in the middle are 2. And we can see that why that happened, because up here we had, like, for example, 4 times 5 and 3 times 4. So those are separated by 2. So now we can write this as simply 1 plus 2 times 2 plus 4 times 2. And what we're going to have is these 2, 4, and so on. These are all the even numbers. The reason for that is, for example, we have 2, 2, 4, 4, 6, 6, and so on, and 38, 38. So all the even numbers are there, and then the odd numbers to the left and right of each even number appear over here. So the point is that the sum is now 1 plus 2 times 2 plus 4 times 2 all the way plus 6 times 2 all the way till 38 times 2 minus 39. Now, this is pretty easy to evaluate. We can basically group this 2 times 2 plus 4 times 2 and so on. We can remove a 4 from each of them. We can factor out a 4 because all of them are divisible by 4. It'll be 4 times 1 plus 4 times 2. This is 8, which is 4 times 2. This is 12, which is 4 times 3, and so on. And this is 38 times 2. So if you divide that by 4, that's 19. So, and then we have the plus 1 and minus 39. So it's 1 plus 4 times 1 plus 2 plus 3 all the way till 19 minus 39. And this is just an easy computation. We have 1 minus 39, which is negative 38. And then we add on 4 times 19 times 20 over 2. This is 19 times 20 over 2 because it's a very important formula that 1 plus 2 times 3 all the way till n is n times n plus 1 over 2. And then finally computing this, the answer is 722. So looking back, recapping, the main idea was that we can take advantage of all these equal numbers that are appearing in sort of similar order by using the distributive property. So we can line them up in this table right here is sort of the main idea. If you're writing it on your scratch paper, you might also write down a similar table. And then the main idea is that when you subtract, you just subtract each column and then numbers factor out. So you have like 2 times 3 minus 1, 4 times 5 minus 3, and so on. And then you can factor, and then you just get a very simple expression compared to what we've been dealing with, from which you can easily finish. So if this was confusing, again, refer to the handout. We'll be updating the handout to fix typos and make things a bit clearer, but the handout is there. We're also going to add the recording for last week's class and this week's class. Last week's class is also on YouTube. You can subscribe to our channel if you also want to get notifications, but we do upload onto the website, so that's subscribing is not necessary, but we're going to add it to the chart right now. And yeah, so we'll get the handout, the recording for last week and this week. And one thing we wanted to talk about was that we're planning an event for this Sunday, so the upcoming Sunday, which is January 31st. Since the Math Counts chapter competition is coming up, it's in less than 2 weeks. We thought we should go over a few strategies and tips and experiences that we had and so on. So that should be pretty fun and helpful. That's going to be for an hour on the 31st of January at noon. And that's going to be at noon on Sunday. We are going to send more details to everybody shortly, but it's on the website. Yeah, noon PST, that's correct. We're going to send more details to everybody by email. And yeah, but stay tuned. Please join next week, Sunday, noon, again, that is. We're going to send a flyer and Zoom link and all that, but yeah, just register. And yeah, I think that's it. I hope everybody enjoyed the class, learned from it. Anything else you can think of, Nivid?
I have nothing to add, but yeah, thank you everybody for coming, and I hope you all learned something today.
All right.
Thank you. Bye.
Thank you all for coming.
Thank you. Bye.
Thank you.
so much
Bye.
for coming.
Thank you. Bye.
Thank you. Bye.
All right. I'll end the meeting now.
All right, sounds good.